Just bear with me one moment. Okay. And so the official title of this course is actually Radiopharmacy and Nuclear Medicine Physics. My name is Dr. Stephen Karish, and I have a business of being a consultant to nuclear medicine departments literally all over the world, mostly though in the United States. And all the slides that you're going to be seeing shortly were reviewed and revised just about 10 days ago. I finished it on January the 5th. Your program director should have sent you this file as a PDF file. You're welcome to follow along with the lecture notes from that file that was sent to you earlier. Just a very brief biography. I took my entire resume and put it on one slide for you so you won't be too bored. But I have a college degree in chemistry, College of Charleston, a master's degree in radiochemistry from Clemson University, home of the famous Clemson Tigers. And I finished my doctorate at the University of Maryland in College Park. Did a little postdoctoral research. And for the last 38 years, I've been a professor in the radiology department at Loyola University Medical Center, which is right outside of Chicago in a town called Maywood. I've had many, many years of experience teaching students and technologists and physicians and pharmacists. And I have also run as the course director over 100 nationally advertised courses that focus mostly on the basic science of nuclear medicine. You might be interested to note who is participating in this Zoom lecture series, and we have 6 programs from all over the United States. We have Chattanooga State in Chattanooga, Tennessee, the College of DuPage and Triton College, which are in Illinois, Galveston College in Texas, Gateway Community College in New Haven, Connecticut, and Santa Fe College in Gainesville, Florida. And we welcome all of you to the program today. You should have a copy of this lecture schedule, but basically we're going to be meeting from 9 to 11 a.m. every Tuesday for today and the next 13 consecutive Tuesdays. So we'll be starting January 14th, finishing April 15th. And for any reason we have a schedule disruption, then we have added on an extra date for April 22nd. Hopefully we will not use that, but at least it will be there if we need it. So we're going to officially start with the slides. This is the very first one. You all know what nuclear medicine is, but I wanted to define a couple of key words for you that might give you a little bit more insight. It is certainly a multidisciplinary specialty. You have to be good at physics and chemistry and mathematics, biology, electronics, a little bit of nuclear chemistry, analytical chemistry, image processing, and other things I can't even think of at the moment. And in fact, one of the bonuses of having such a tough specialty from a scientific standpoint is that the most highly paid technologists in the hospital are typically nuclear medicine technologists and MRI technologists. If we take a look at the importance of nuclear medicine, it is certainly a vital part of managing patients, both diagnostically and therapeutically. And in fact, JCAHO, that is the Joint Commission on the Accreditation of Healthcare Organizations, that's the regulatory body that comes in and inspects our departments literally every 36 to 39 months. And when they issue a certificate of approval, we then can open our door and accept patients. And one of the things to note in the charter is that JCAHO will not even accredit a hospital unless nuclear medicine services are provided. So that's a mandatory thing. Now, this is the first of probably 200 or 300 questions that are integrated into these lecture notes. And anytime that you see a question, the answer will be on the next slide. So would anyone like to take a guess? What percent of all nuclear medicine studies are therapeutic and what percent are diagnostic? Anyone?
I feel like they're mostly diagnostic. As to a percentage, I'm not sure.
Okay.
Maybe 90?
Is it roughly about 1% therapeutic?
That's actually not a bad guess, but this is probably a little better average. Somewhere between 95 and 98% are diagnostic and 2 to 5% are therapeutic. So I'm going to give you all credit for answering that correctly. Think about this. We all work in teaching hospitals primarily, and teaching hospitals do a lot of therapy, but the majority of hospitals in the United States are actually community hospitals, and many of them do no therapy at all. And that really skews the average a lot. So perhaps at my hospital, we do 10% therapy, but many others do much less. So I think 95 to 98%, it's a pretty good range. Also, and I think this number is a little old, it says there are approximately 20 million imaging studies performed per year. I think because of PET scanning, that number is a little bit higher now. It's probably closer to 25 million, but that is simply imaging studies. That does not include things like radioimmunoassay or in vivo but non-imaging studies like a thyroid uptake test. This number kind of interested me. Roughly 1 in 7 hospitalized patients will undergo a nuclear medicine procedure of some kind. I would have thought much less, but especially in teaching hospitals, it's a pretty significant percentage. Most important thing on this slide is this last point here, and we're going to expand this on the next slide. There are 4 kinds of studies that we perform. There are static images, and we'll define that on the next slide, dynamic images, in vivo but non-imaging studies, and finally, completely in vitro studies. And here are some examples of those. A static image is one where there's no change in the image as a function of time. For example, if we do a liver scan and take a picture at 10 minutes or 1 hour or 2 hours, all those pictures are going to look the same. The dynamic phase is long over, and we are now looking at the static scan. Also a bone scan, 3 hours down the road or 4 or 5, the image is going to look very, very similar. On the other hand, we have dynamic imaging where the image does change as a function of time. Examples might be a MUGA, where we're literally watching the heart beat on the screen, and we have a roughly 1 second cycle time, or a pulmonary ventilation study where the cycle time is longer, or a renal scan. We have what are referred to as in vivo but non-imaging studies. Who knows what RAIU stands for? Anyone? You should know.
Radioactive iodine uptake.
Thank you, that's perfect. So that is an acronym that sometimes appears on the exam and they don't define it for you. So you should know that this stands for a radioactive iodine uptake. That is a non-imaging kind of study. Or if you do GFR kidney studies for glomerular filtration rate, that's also a non-imaging study where we will be perhaps sampling blood and urine, but not taking any pictures. And finally, something that we rarely do anymore, most nuclear labs don't have a radioimmunoassay lab. We had one at Loyola for years, and we were performing hundreds of RIAs per week. And the next thing we know, along came immunofluorescent techniques, and that was the end of RIA. It's not completely the end, but very few departments actually do these kinds of studies anymore. Now, this is an important slide because it highlights the differences between nuclear medicine and all of the other radiographic modalities. We are doing what are called functional studies. We only care about what is the percent uptake in the target organ as well as the other organs in the body. How fast is it clearing through the kidneys, through the liver? We need to know the biological distribution everywhere, and that's because we are looking at organ function, and we don't care too much about tissue density differences. On an X-ray, tissue density differences make all the difference in the world. Muscle and fat and bone have different densities, and that's why we can easily differentiate them. We are working on a molecular level, and one of the beauties of that is that we can often detect disease much earlier than any other modality because we don't have to wait for an anatomical change to appear on a scan. we are working on that molecular level. Common exam question is the following. Which is going to find metastatic bone disease first, a bone scan or a radiogram? And the answer is that the bone scan will find it months or sometimes years before it shows up on a radiogram. So the beauty of that molecular imaging is that we can often make the diagnosis earlier than any other modality. Now, there's a famous and very old joke that if you take nuclear medicine and rearrange the first two letters, you come up with unclear medicine. And it is partially true in the sense that the resolution of our scans can't compete at all with MR or CT. We can't find pulmonary nodules that are 2 millimeters in diameter, but we can still find disease earlier than any other modality often, not all the time, but often. And we'll see some examples of this later on in the radiopharmacy section. So here would be your question: which type of study, anatomic or molecular, is most likely to make the diagnosis earlier? And you know the answer to that. Okay, now that's all introductory material. And I wanted to review with you now some of the basic definitions. We want to take a look at atomic structure, and anyone who has ever taken a chemistry course, which is probably most of you, if not all of you, have seen a diagram that looks very similar to this. This is a sketch of one atom. You'll note here in this white area in the geometric center of the atom is what we call the nucleus, and contained in the nucleus are protons and neutrons. And collectively, we call all of these particles that live in the nucleus nucleons. So if anyone asks you how many nucleons are present, you're going to add up neutrons and protons, and that would be the total. So here in this very small region is the nucleus. Surrounding it are shells. I'm only put 3 here, but there are lots more. The KLMNOP shells that are surrounding the nucleus, and that's where the electrons live. You can see a couple of them just sketched in right here. Now, in the shells, there are orbitals, and we're going to take a look at the different orbitals and the structure of them. So let's take a quick look here. We have the KLMN shells, and within the orbitals are S, P, D, and F orbitals. Those are the designations of the orbitals. The S orbital can hold only 2 electrons, the P can hold only 6, the D can hold 10, and the F can hold 14. Those are unchangeable numbers. They never change. And if you recall, maybe a few years ago, your chemistry professor asked you to sequence the first, let's say, 20 or 30 electrons, you would have seen something like what's on the bottom here. 1s2, 2s2, 2p6, 3s2, and so on. So what does 3p6 mean? It means that in the third shell, that's the 3, in the third shell, the M shell, but in the p orbital, there are 6 electrons. 3d10 in the third shell, there are 10 electrons in the d orbital, and so on. Now, if you have your lecture notes in front of you in paper, I would ask you to put a star by this slide. This is a very common exam question. What is the formula for the maximum number of electrons that can fit in one particular shell? Anyone know?
2n square.
You choice A?
Yeah.
Yes, correct. So it's 2n squared. Now, 2n parenthesis squared is the same as 4n squared, and those two are both therefore wrong, and this would be 16n squared. That's totally wrong. Correct answer is 2n squared, and here's how that could be manipulated mathematically. Here are your 5 shells, shells 1, 2, 3, 4, 5. We simply take the number 2, multiplied by the square, excuse me, the square of the shell number 1. So in the K shell, we can only put 2 electrons. In the L shell, we have 2 times 2 squared, that would be 8. In the M shell number 3, we have 2 times 3 squared, that's 18. And even down here on the bottom in the 5th shell, the O shell, we have 2 times 5 squared, 50. So these are the maximum number of electrons that will fit in the first 5 shells, 2, 8, 18, 32, and 50. Now, for any nuclide X, X is any element in the periodic table. And as you probably know, there are over 100 elements now, somewhere about 110 that have been defined altogether. And the elements X have 3 numbers associated with them. There is the Z number, which is the number of protons. And in a neutral atom, it also equals the number of electrons in the outer orbitals. I have no idea why it's a Z. If I were designing this, I would have put it as a P for proton, but that's not what they do. So the Z number represents the number of protons in the nucleus. It's the number of electrons, and it's also going to identify the position in the periodic table. If Z number is 20, that's element number 20. That would be calcium. N is the number of neutrons, and A is the atomic mass. And to get the atomic mass, we simply add up N plus Z. If you look down here on the fifth line down, the number of neutrons is A minus Z, and that's because the atomic mass is the number of protons plus neutrons all together. Now, there's a commonly asked board question, and here's how it goes. The next to the bottom line, N equals which of the following? A minus Z, that is, of course, the correct answer. How about Z minus A? The absolute value of Z minus A would be equal to the absolute value of A minus Z. But if you have Z minus A, it gives you a negative number of neutrons, which is impossible. Another bad choice might be A plus Z over 2. Wrong. So the correct answer here for the number of neutrons will always be A minus Z. That's right here. A minus Z will give you the number of neutrons. And so the nucleons would be the total number of particles in the nucleus. That would be neutrons plus protons. Now, this is a small piece of the chart of the nuclides. I want you to don't think that this is part of the periodic table. Not at all. What this chart of the nuclides does is it lists every single nuclide, every single isotope for a particular element. For example, in number 8, oxygen, this says that 15.9994, which of course we round off to 16, is the weighted average of all known oxygen atoms that are naturally occurring in this universe. And these 3 over here with the grayed background, oxygen 16, 17, and 18, they have in here the percent abundance. This is 99.7, 0.037, 0.204. These 3 here, which have a white background, are radioactive. They don't have percent abundances. They don't occur naturally. Instead, they have half-lives, milliseconds, seconds, and seconds. Now, that's what a piece of the chart looked like 40 years ago. This is what the new chart of the nuclides looks like. I just captured this from the internet a couple of weeks ago. And you can see down here at number 8 that there are now some other isotopes of oxygen that we never knew existed. I never heard of oxygen 19. And sorry, I think I was looking at the wrong line. So I'm sorry, up here. We're up here. I've never heard of nitric oxygen, 19, 21, 22, 23, 24, 25, 26. Some of these have half-lives of nanoseconds. That's trillions of a second. So this chart has been updated. It's nice and color-coded, and anything that's in this light blue color here is stable, and every other color, including white, is unstable. And the color coding has to do with the half-lives of those nuclides. Now, each of those little boxes contains a wealth of information. I've magnified one box just to give you an idea of what's in there. Magnesium 28, that is, of course, a symbol and the mass number. This is the half-life, happens to be in hours. This is both a beta and a gamma emitter with the energies listed here. the disintegration energy is 1.84 MeV. That means that as magnesium-28 decays to its daughter, it's going to give off a total of 1.84 MeV, regardless of the route that it takes going from the parent to the daughter. Now, we're going to take a close look at the ISO terms. ISO means same. Some of these we have a pretty good word association. For example, isotope. Tope has a P. Protons, iso P. It's the same number of protons. Now, read this sentence very carefully. Nuclides that have a constant Z number, a constant number of protons, are going to have different A numbers and N numbers. The only thing that will be constant will be the number of protons. And here's an example. Here's calcium 2040, 2042, 2045. These all have the Z numbers of 20, but you'll note that the atomic masses all are variable. And the number of neutrons, we don't ever write that down, but it should be very easy for you to calculate. What's the number of neutrons going left to right? How many here? Anybody? Just do the subtraction. This is going to be 20 neutrons, 22, and 25. So what should be obvious is that the number of protons is constant, the atomic mass is variable, and because we did the math, the number of neutrons is also variable. So the only thing constant is protons. Isotones, tone has an N in it. That implies it's a constant number of neutrons. And when you look at a series of isotones at first glance, they look like they have nothing in common whatsoever. These numbers are variable and these numbers are variable, but do the subtraction and what do you get? You've got 22 neutrons here, 22 here, and 22 here. This is therefore a series of isotones, and they look like they have nothing in common, but in fact they do. If we wrote the number of neutrons, you'd recognize right away that they were isotones. And finally, isobars. Now, the word association is not so easy here. We don't have a P or an N standing for proton or neutron. The best thing to do to help you here is isobar has an A in the middle. And so here we have a constant A number. The atomic mass is 40 for all three, but you can see that the number of neutrons is variable. And when you, the number of protons is variable. And when you do the subtraction, this has 22, 21, and 20 neutrons. So those are isobars, constant mass number, but variable other numbers. Now, I'm going to give you 3 little questions here. Hopefully you'll be able to give me an answer in a moment. And then I'm going to show you a couple of old board questions. So what do these have in common? Each of these terms has one number, a constant, and the other 2 numbers must be variable. The 4th term is isomer. I don't have any word association for you at all, but if you think about what we know about technetium down on the bottom, the mode of decay is called isomeric transition. It's a transition from one isomer to another. So these are 2 identical atoms. All the numbers are the same. They both are number 43. They both have an atomic mass of 99. And if you do the subtraction, they both have 56 neutrons. So what's the difference? If they have all the same numbers, the difference is that technetium 99M has an excited nucleus, and the technetium ground state, that's the G is for ground state, has a de-excited nucleus. That's the only difference. They have different nuclear energy levels, but chemically they are identical. Chemically they are inseparable. There's no way, and physically also, there's no way to separate an isomer from another isomer. Simply, we can't do it. Now, that M stands for metastable state. I want you to look carefully at this definition because there is a good exam question that comes from this. We define a metastable state as an excited state that has a measurable half-life. That is the definition of the excited state, a measurable half-life. And measurable by convention means a microsecond or longer. A microsecond, millisecond, a second, a minute, hour, a day, a week, a month, a year, whatever. So all the numbers are the same, And so the decay is going to be by the process of isomeric transition to the ground state. Now, here's a good question for you. We know that isomers have all their numbers in common, but what do you think about this? What do isomers have in common related to the decay, mode of decay, the energy, the half-life? Which of those would be constant?
Nothing?
Which one?
None of them?
Great, none of the above. That's excellent. Let's take a look at the numbers. Technetium, metastable, and ground state, look how different their half-lives are. 6 hours and 220,000 years. Technetium is a pure gamma ray emitter with isomeric transition. Ground state is both a beta emitter and a gamma emitter with lots of gammas and a pretty high energy beta. So they have nothing in common regarding their emissive properties, nothing at all. But as we said earlier, all their numbers are the same. Now, we have 3 little quiz questions here and then a couple more to follow. In that black oval, we're looking at molybdenum 98 and technetium 99. What is that? That's a pair of what? Isotopes, tones, or bars?
Isotones?
Excellent. Those are isotones. They have nothing in common at all, except if you do the subtraction, the number would be 56. How about this pair in the black oval? We have molybdenum 99 and technetium 99.
Isobars.
That's a bar.
Good. Isobars. And how about this pair? That should be the easiest one.
Isotopes.
Sure. If they're the same element, they have to be isotopes. Now, I use this as a teaching tool. You're not going to get a question on an exam that looks like that, but that's a good way to learn it. Here's what your exam question is going to look like. I want to caution you, when you're taking your exam, read every possible answer. And this, in particular, in this question, it makes a lot of difference if you read all the possible answers or if you don't. Which of the following consists of isotones? So you have choice A, B, C, and look what choice D is, A and C. So if you thought choice A was correct and didn't read any further, you might have missed the question. But who knows? Which one of those would be isotones? A, B, C, or D? Who's got it? I heard a B. Good. Sure. These are isotones. Remember, they look like they have nothing in common, but when you do the subtraction, you'll see that it's going to be, I think, 88, whatever that number happens to be. Those are the tones. What about this question? Which of the following would be isobars? Bar has an A in it, a constant mass number.
Is it D?
Good. That would be choice D, because both A and C have constant mass numbers. And so the correct answer would be choice D, which is A and C. So that's just a good caution for when you're taking the exam. Don't just stop reading if your sure choice is correct. Now, let's see what you do with this. Considering that technetium, metastable, and ground state are isomers, we know that's true. True or false? Since both of these are technetium and obviously have the same Z number, they're also isotopes. True or false?
False.
False.
That is definitely false, and here's the reason. Isotopes have to have 2 numbers variable. Those have no numbers variable. They're both 43, 56, 99. So they cannot be topes, tones, or bars because those require variability in the numbers. And in isomers, we have no variability whatsoever. Now, we want to take a look at all of the different particles and photons that are emitted. We want to learn how to write them, the symbols, the numbers that go with them, their charges, their masses. And there are 4 or 5 little charts here. And these are in alphabetical order. There are 2 ways to write an alpha particle. In fact, all it is a helium nucleus. It's a helium-2,4 that has had its 2 electrons stripped off, so it has a 2+ charge. So how many electrons are in the outer orbital? 0. There aren't any. There were only 2, and they're gone. So this comes out as a helium ion. We don't write the 2+ charge ordinarily. We just write helium-2,4, or totally interchangeable, alpha-2,4. I usually write this one, but either one of these is fine. Helium-2,4 or alpha-2,4. And all the helium in our atmosphere actually resulted from alpha decay. And you might think that because the Earth is 5 billion years old, there should be a lot more helium in the atmosphere, because every alpha particle that's emitted picks up 2 electrons and becomes a helium atom. And why is there so little helium in our atmosphere? All of those alpha emitters that are in the soil have extremely long physical half-lives. And on top of that, the atmosphere is just voluminous. So there's not much out there. It's a tiny fraction of 1%. Next is a beta minus particle. We have 2 ways to write this. E minus 10, that is, the charge is -1, but the mass is 0. Now, is the mass of an electron truly 0, or is it just a very tiny amount that approximates 0? And the answer is, it's really not 0. It's really 0.00005. There should be 4 zeros, 0.00005 of 1 atomic mass unit. So it's very tiny. It's one of the basic particles, and it has no nucleus at all. We could write this as either E minus 10 or beta minus 10. As particles go, they are identical. So what is the difference? Here's your board question. What is the difference between an ordinary electron and a beta minus particle? And the answer is the origin, or the source. Electrons are found only in the outer orbitals. Beta plus beta minus particles may be emitted from the nucleus because of a disintegration that takes place, but there aren't any there. But as we'll learn later, beta minus particles can be emitted from the nucleus. And the only difference between those particles is, other than energy, is where they came from. There also are beta plus particles. We consider beta plus particles antimatter to ordinary electrons. And in fact, when this beta plus particle here interacts with this beta minus particle here, or an ordinary electron, what is that reaction called? What happens when a positron strikes an electron? What's that reaction called?
Annihilation event.
Sure, that's an annihilation reaction. And I'm going to go ahead for one moment to show you this is what it looks like. A positron strikes an electron. They literally destroy each other. They produce 2 photons that are always 511 keV, regardless of what this positron energy is. They're always going to be 511 keV, and the angle between them will always be 180 degrees. Let me just go back, make sure I didn't leave anything out. I don't think so. The mass of this beta plus particle is identical to the mass of this beta minus particle, 0.00005 of an atomic mass unit. The only difference is this is positively charged. And antimatter has very short lifetimes in this world, usually seconds or milliseconds or microseconds. So when those 2 collide, they lose, and they only collide when the positrons have very minimal kinetic energy. What happens if an energetic positron hits an electron? It does not annihilate it. It knocks it out of the way, creates an ionization event, but it doesn't annihilate it. It has to cool off and reach close to its rest mass, its point of lowest kinetic energy, and only then will this annihilation take place. Next is a gamma ray. The gamma ray is written only one way. There's no interchangeability. A gamma 00, the charge is 0, and the mass is 0. So your board question is the following. what's the difference between a gamma ray, which is gamma 00, and an X-ray? We could write this as, as X00. What's the difference between a gamma ray and an X-ray? Our gamma camera can't tell the difference. When we're doing thallium imaging, we're often collecting and imaging X-rays. The camera can't tell the difference. What's the difference? The difference, again, is the source. Where do gamma rays come from? Only. They come from the nucleus. Where do X-rays come from? Only. They come from outer orbitals. Other than that, there is no difference. Their interaction with matter is the same. They are ionizing radiation. They cause exactly the same kinds of reactions. So just keep in mind that gamma rays and X-rays are identical except for their source. Neutrons, only one way to write neutrons. That symbol would be N01. The charge is 0 because it's neutral, and the mass is 1 atomic mass unit. And lucky for you, there is no such thing as neutron decay, spontaneous neutron emission, nor for protons is there spontaneous proton emission. So we don't have to worry about neutrons or protons being released as a result of decay. We do have to be concerned with bombardment reactions of the cyclotron, but not decay. So neutrons only in the nucleus, neutral, charge is, the mass is 1. Which is larger in mass, a neutron or a proton? And that would be the neutron. The difference in the mass of a neutron and a proton is almost, but not exactly, the mass of an electron. So that difference is 1 part in about 1835, just a very tiny difference. Proton, just like the neutron, found only in the nucleus. This positive charge is always counterbalanced by an electron. We know that if there are 20 protons in the nucleus, there are going to be 20 electrons in the outer orbitals. Now, hydrogen, a hydrogen atom and a proton are basically the same thing. It's P11, it's H11. There are 3 isotopes of hydrogen, and only 3. One is H11. So if we look at H11, how many neutrons are in a hydrogen atom? Anybody? Hey, do your subtraction.
0.
0, H11, 0. But how about deuterium? Deuterium is called heavy hydrogen. Deuterated water is called heavy water. And that would be H12. So how many neutrons here? We would
1.
have 1, good, because 2 minus 1. And tritium is H13. That one has 2 neutrons. And of all the known nuclides that exist, tritium has the highest neutron-proton ratio, 2 to 1, of anything, any isotope you will ever encounter. And that's why it's unstable. The neutron-proton ratio is too high. And in that case, we would predict it would be a beta minus emitter. And it is. And in fact, tritium has a 12-year physical half-life. Okay, any questions about any of those particles? Okay, good. Next is a very, very important term for you to understand attenuation of radiation, for you to understand how to protect yourself from radiation and which radiations are more dangerous to you and which are less dangerous. You need to know what LET means. It defines the term linear energy transfer. And what that means is, what is the fraction of energy deposited per unit distance of travel? It's usually in terms of keV deposited per micrometer of travel. And we'll take a look at a small chart shortly, just to give you an idea of relative keVs of alphas and betas and gammas and X-rays. So again, it's the fraction of energy deposited per micrometer of travel. So if the LET is high, that means it's going to dump all of its energy in a short distance of travel. And so it's going to be probably the most risky thing that you can have in your body. Something like an alpha particle. You don't ever want to be injected with an alpha particle. It only goes micrometers. It has a very high LET. It's going to deposit all of its energy in a distance that would be thinner than one sheet of paper. So the LET is going to be inversely proportional to how far it can travel. And penetrability means how far it can travel. And so the LET is going to be inversely proportional. We'll take a look at an example of that in just a moment. Now, this will give you a little bit more insight about the attenuation of alphas, betas, and X-rays and gammas. I'm going to call X-rays and gammas in this diagram. An alpha particle has a very high LET. It can only go micrometers. That's it. An alpha particle cannot penetrate your skin. It cannot even go through one sheet of paper. It doesn't go anywhere, basically. A beta particle has a high LET, much higher than a gamma, but much lower than an alpha, but still we consider it high. And so beta particles only go millimeters. So now I'm going to hold my fingers up and hopefully you'll be able to see the difference here. A beta particle can perhaps go 1 centimeter. An alpha particle, I can't even get my fingers separated by that distance, maybe 10 micrometers. And so while you're looking at fingers and saying, oh, that doesn't look so different, it's a factor of 1,000. Beta particles, even though they're not very penetrating, are 1,000 times as penetrating as alphas because they go millimeters, which is 1,000 times as large as micrometers. And finally, the gamma rays are very penetrating. They have a very low LET, and they will travel or traverse through tissue many centimeters. If you have a large room that's 20 feet by 20 feet, and you put a source of technetium in one corner and go diagonally across the room so you're 25 feet away with a Geiger counter, you're going to be able to detect it because the LET of gamma rays in air is very, very low. Air doesn't stop gamma rays very much. So we're looking at micrometers, millimeters, and many centimeters. Now, this is just a sketch. It is not to scale because I can't do micrometers to scale, but it just shows you that an alpha particle is not penetrating at all. A beta particle can go some distance up to perhaps 1 centimeter or 10 millimeters, and gammas can go really, really far. Just try to give you a human perspective of how these travel through human tissue. Now, just to show you some numbers, gamma rays and X-rays have LET values that are low, 0.2, 0.3, or 2, low numbers. High energy protons, you might have heard advertising on the radio about proton beam therapy. 10 million electron volt protons have an LET of almost 5. High energy neutrons, 12. Look at alpha particles, close to 200, compare 200 to 2. And giga electron volt metal ions can go way over 1,000 LET, but we're dealing really down here with the X and gamma and also beta particles, which are going to be somewhere close between 2 and 5. Now, I have a half a dozen quick questions for you relating to what was in the chart with the alphas and betas and neutrons and protons, and also relative to LET. Now, I've been using these questions for many years, and I've had some of the smartest people I know, many doctors even get some of these wrong because they're not thinking correctly about increasing and decreasing. So before you answer that question, think about increasing or decreasing. Here's your first question. How would you rank alpha, beta, and gamma in order of increasing LET? Would it be alpha, beta, gamma, beta, alpha, gamma, alpha, beta, beta, gamma, alpha? You got 6 choices. How would you rank this in order of increasing LET?
Gamma, beta, alpha.
Good. Gamma has the lowest LET, beta in the middle, and alpha is the highest. How about this? How would you rank these 3 in order of decreasing penetrability?
Gamma, beta, alpha.
Good. Remember, the first question said LET. Highest LET goes with the lowest penetrability. So again, the decreasing penetrability would be gamma, beta, alpha, because gammas are the most penetrable and alphas are the least. How would you rank these in order of increasing range and matter, assuming they all had the same energy? Increasing range and matter.
Alpha, beta, gamma.
Good. Alpha, beta, gamma. That's because it's micrometers, millimeters, and centimeters. How would you rank these in order of increasing atomic mass?
Gamma, beta, alpha.
Perfect. Gamma has a mass of 0, beta has a mass of slightly more than 0, and alpha has a mass of 4 atomic mass units. Good. Now, I think this is probably most difficult of these questions. How would you rank alpha, beta, gamma in order of increasing charge? All right, I want to give you a hint and aim you in the right direction here. We're not talking about the magnitude of charge, like is it 1 or 0, 1 or 2 or 4, anything like that. We're talking about the increasing charge from negative infinity through 0 to positive infinity, going on the number line from negative to positive. How would you rank those in increasing charge?
Would it be beta, gamma, alpha?
Sure. Beta is a negative number, gamma is a 0, and alpha has a +2 charge. Remember, it lost its 2 electrons. It's a positively charged particle. How would you rank these in order of decreasing risk to the patient for an equal activity that would be injected?
Alpha, beta, gamma.
Yes, a decreasing risk, sure. Alpha is by far the riskiest. You never want to be injected with an alpha. You know for sure that 100% of its energy is going to be deposited in your body somewhere. The gamma, on the other hand, the amount deposited in the body is usually 10 to 40%. So most of it is escaping and interacting elsewhere. Okay, now you won't get this exact question on a board exam, but you might get some part of it. So let's consider for technetium 9943. It's going to go down the list. How many neutrons?
56.
56,
56. How many protons?
43.
43.
43,
Good. Electrons, assuming it's a neutral atom, electrons.
43,
Positrons.
0.
Good. 0. Positrons don't live in the nucleus. So the question always comes up, well, how can a nucleus with no positrons emit positrons? We're going to learn later that a proton disintegrates, forms a neutron, and emits a positive electron. So the answer to this is 0 live there. How many freons? Okay, I just made that up for fun. There aren't any. Okay, how many nucleons?
99.
99.
99. Atomic mass,
99.
atomic number.
40.
43,
Excellent. So there are your answers to those questions. Atomic nucleus has 39 protons and 50 neutrons. What's its atomic mass number?
89.
89,
89. Choice D. Good. We simply say A equals Z plus N. And remember that A also equals the number of nucleons. How about this one? We have bromine 3573. How many neutrons?
38.
A, 38, correct. Just simple subtraction. Okay, the fundamental particles that we've been learning about are the proton, the neutron, and the electron. Now, we're going to go down this list, and for each half of the statement, we're going to say, is that half true or false? And then the one which has both true will be the correct answer. So choice A, of those 3 particles, the electron is the least massive, true or false?
True.
That is true. Remember, the electron is almost zero in mass, certainly the least massive, and it has a negative charge. That's also true. Therefore, choice A is the correct answer. But let's look at why the others are wrong. The proton is the least massive. That's false. Proton has a negative charge. That's false. The proton is least massive. That's false. Has a positive charge. That's true. The neutron is the most massive. That's true. Positive charge. That's false because it's neutral. So choice B. Good. How about this? A nucleus decays by emitting a photon. The metastable state of technetium decays to the ground state. And by the way, you're not going to ever see the G anywhere else. I'm only using it as a teaching tool. When you see technetium 99 without the G, that means 220,000 year half-life. It's not the metastable state. Okay, so we have the metastable going to the ground state. Parent and daughter nuclei are,
Isomers.
Isomers.
those are isomers, right? They can't be topes, tones, or bars. Those require variability. So it cannot be therefore a combination of two of those. It's only isomers, choice D. Isomers can never be topes, tones, or bars. In beta minus decay, which of the following is emitted? An ordinary electron, a positron electron pair, or annihilation radiation? Who's got it?
A.
Choice.
Ordinary electron.
That's correct. An ordinary electron. It just happens to be coming from a nucleus and not the orbital. But remember that a beta minus particle and an ordinary electron are identical physically. So choice A. Okay, let's mark these as true or false. The Z number represents the number of protons.
True.
True.
The Z number represents the number of electrons.
True.
True.
True, in a neutral atom, but we're assuming we have a neutral atom. True. The neutron number is represented by parenthesis Z minus A.
False.
False. How would we correct it?
A minus
Z. Good. A minus Z would correct it. Electrons in outer orbitals are electrically balanced by positrons in the nucleus.
False.
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 False. Excellent. I can't tell you how many people have thought that is true, but the balance is by protons and not positrons. And finally, the mass number A equals, in parenthesis, 2Z plus N.
False.
False.
False. Should be Z plus N. So there are your answers. Okay. Gamma rays are most similar to which of the following?
X-rays.
Good. Now, X-rays, of course, is the correct answer. And let's take a look at why. First of all, you could throw B and D away. High-speed electrons and sound waves are not electromagnetic radiation like the rest of them. X-rays and IR and laser beams, those are electromagnetic. So A, C, and E are electromagnetic. They all travel at the speed of light. And you might think, well, they're all similar, and that's true. But the one that's most similar is X-rays, because unlike these two, X-rays are ionizing radiation. And that's what makes them most similar. Okay. The technetium nucleus is a metastable state of technetium. I'm going to give you a minute just to read through those answers. I'm not going to read them to you, but take a minute to read it, and then who can tell me which is the correct answer, A, B, C, or D? Okay, anybody got it?
C.
C.
Correcto, definitely. Isomeric transition means that a photon is going to be emitted a measurable time after its formation. That means that the half-life is going to be measurable, a microsecond or longer. So choice C is correct. Okay, the decay of metastable ground state is an example of
E.
C, isomeric transition. Good. Okay, now let's take a mental pause just for a moment. Any questions about anything that we have covered so far? Okay. Okay. If not, we're going to take a look at completing nuclear equations. Now, 5 minutes from now, I am hoping you will think, I pray to get one of those on the board exam because there's no reason to ever miss one. The rules are very, very simple. The Z numbers on the left have to add up to the Z numbers on the right. The A numbers on the left have to add up to the A numbers on the right. And we're going to take a look at an example of that right now. We have two kinds of reactions to deal with. One is a simple decay reaction like this. That is, uranium-238 decays by alpha decay and produces a daughter. And your exam question would not be, what is that daughter? Without a periodic table, you wouldn't know, and I probably wouldn't know either. The question would be, what are the A and Z numbers of the daughter? So we're going to say that the A numbers on this side have to add up to this side. So 238 equals 4 plus 234, and 92 equals 2 plus 90. So the numbers here will be 90 and 234. Very simple math. 238 equals 4 plus 234. 92 is 2 plus 90. That's a decay reaction. Now, I want you to note the terminology here because it's different from a bombardment reaction. Here, we have a parent decaying to a daughter. In a bombardment reaction, we don't have a parent or a daughter. We have a target and a bombarding particle that gives us a product and an exiting particle. So here we're saying the uranium is bombarded by a proton, out comes an alpha particle, and the product is protactinium-235. And look at the math. 238 plus 1 equals 235 plus 4, balanced. 92 plus 1 obviously equals 91 plus 2, also balanced. Now, when you take your exam, you're not going to get this in this format. It would be easier to work the problem this way. But by convention, nuclear bombardment reactions are written in a condensed format that looks like this. In the middle is parenthesis. It's parenthesis containing the bombarding particle, comma, the exiting particle. So if I saw this equation here, if I saw this equation, I would rewrite this equation like the top equation. That is uranium plus a proton, here it is, yields an alpha plus protactinium, here that is. So when I'm going to give you a practice problem in a moment with one like this, and you want to expand that equation before you do the math, I advise you to not work that in your head. Could you do it? Maybe, but you're more likely to miss it this way than by expanding it. Now, before we look at those equations, for any given target, there are probably 40 or 50 different reactions, bombardment reactions that could take place. Some of them are simple. What is an NP reaction? Neutron is the bombarding particle. The proton is the exiting particle, used all the time. Or you could have an alpha P reaction. Bombard with an alpha, out comes a proton. Some of these, however, are pretty complicated looking. What does alpha comma P4N mean? We obviously are bombarding with an alpha, but what does P4N mean? Is it producing a proton and 4 neutrons? Is it producing 4 protons and 1 neutron? Or is it producing a particle called a P4N product? What is it? Anybody? So this is going to be the reaction where an alpha does the bombarding and out comes a proton plus 4 neutrons. And I'm going to give you one of those shortly in your little practice test that we can take a look at in class. So now I'm going to make the assumption that you do not have pencil and paper in front of you. And so we're going to simply work these in our head, but kind of out loud. calcium 20 decays by beta minus emission and produces X. So what would be the atomic mass of X?
45.
45, right? 45 minus 0 is 45. Now be real careful with this one. Believe it or not, more people get this one wrong than any of those 4 problems. What is the Z number here going to be?
21. Will it be 21?
Say it again.
21.
21. Good. That is the correct answer.
Sweet.
You can see it right here, 21. A lot of people have put 19 as that correct answer, but 19 minus 1, last time I checked, did not equal 20. So good. And there's a lesson built into this problem here. Let me go down for one moment. Anytime you have a beta minus emission, the Z number always increases by 1. It'll go from 20 to 21. It'll go from 40 to 41. It'll go from 60 to 61. In all beta minus decays, Z number always increases by 1. Right? This is a very easy one. Uranium-235 decays to thorium-231 plus X. What would be the A and Z numbers here?
4 and 2.
And therefore, what would that be? If it's got a mass of 4 and a 2
Helium?
protons.
Alpha particle.
Sure, this is nothing but an alpha particle. You can see right, let's see right here in the answer key, okay? How about this one? Now this is a bombardment reaction, an expanded one. We have uranium-238 is bombarded with an alpha particle. Out comes a neutron plus X. So what would be the A and Z numbers of X? What's going to be the atomic mass? Okay, this is going to be 242 minus 1 is 241,
41.
right? And 92 plus 2 is 94 minus 0 is 94. So that's going to be 94 to 41. And now this last problem, protactinium-236 undergoes an alpha comma P2N reaction. Alpha is a bombarding particle, and out comes a proton plus 2 neutrons. And we want to know A and Z numbers of X. And so we're going to take a look at the expanded form, which would be this. We have protactinium plus an alpha 24 yields a proton, if this is blocking your view, I'm sorry, plus a neutron N01 plus another N01 plus X. And so we have 91 plus 2 is 93, minus 1, minus 0, minus 0. And I can't see the answer here, but what would it be?
92.
92. So it'd be 92 to 37. Now, that's one way to get the question. And I think you all understand that the math here is pretty easy. But what if you got this? What if you have to write the equation itself and then come up with the answer? Supposing that all they tell you is that P32 decays by beta minus emission. You have to write the equation. Plutonium decays by alpha emission. You have to write the equation. And one more, technetium decays by IT, isomeric transition. You have to write the equation. So here's how I would do it. If this decays by beta minus decay, I would say P32 yields an electron, E minus 1, 0 plus X. 32 plus 0 is 32. Remember what I told you about beta minus decay? The Z number always goes up by 1. That problem before, we had a 20 going to 21. Here we have 15 going to 16. This was an alpha emission. Plutonium-237 yields an alpha 24 plus X. And by doing the subtraction, 92 to 33. And what about this one? The metastable state of technetium goes to the ground state. And this is going to give off a gamma 0, 0. What else could it be? 99 minus 99 is 0. 43 minus 43 is 0. All that could be is a gamma ray. Okay. Any questions about completing nuclear equations? I think you see that they really are pretty simple if you just are careful. The only two difficult ones would be one like this, a beta minus, and one like this on the bottom here where you have to do the expansion. Okay, any questions? Okay, good. Then we are now going to take a look at an extremely important set of basic concepts. We're going to look at half-lives, and there are 3 of them. And all of us are, of course, most familiar with the physical half-life. How long does it take for half of it to decay? We define it as a period of time to reduce the radioactivity of a level of a parent to half of its initial value as it decays to the daughter. And typically, we just write T1 half. By default, if you ever see T1 half, that is going to be the physical half-life. But when you're comparing physical and biological and effective, then you have to write T-phys like this for T-physical. And here are some things to note about the physical half-life of all isotopes. Number 1, we can measure them directly. Count a sample, we wait, we count it again. We might have to wait a long time, but as long as we have 2 different counts measured over a known period of time, we can either graphically or mathematically determine that physical half-life with great precision. So number 1, we can measure it directly. Number 2, unlike the other 2 half-lives, physical half-life is boundless. It could be anything. It could be as short as a picosecond, a nanosecond, a microsecond, a millisecond, a second, a minute, an hour, a day, a week, a month, a year. It could be anything. Here are some examples. Rubidium-82 has a half-life of 75 seconds. Potassium-40, which we have in our bodies, tiny amount, has a half-life of 1.3 billion years. Half-life could literally be anything. And finally, physical half-life is not affected by any external factors, not even extreme factors such as heating or cooling or pressurizing or putting something in a vacuum. If you take technetium, put it in water, bring it to the boiling point, what's the half-life? It's still 6 hours. Make technetium ice cubes, what's the half-life? It's still 6 hours. Those extremes don't impact physical half-life. Biological half-life has a similar definition. It's also going to be a logarithmic decrease. We define the period of time of biological half-life as a period of time that is required to reduce the quantity of a drug in either a specified organ or the whole body as a function of time. We designate that as T-biological like this. And here's what complicates things. With physical half-life, there's only one half-life. Technetium is 6 hours. That's the end of the story. But here, biological half-life varies all over the place. We can have a biological half-life in the kidneys, in the liver, in the heart, the brain, the spleen, the lungs, and every other organ in the body, as well as the whole body. The whole body biological half-life is going to be the weighted average of the biological half-lives of every organ in the body. So if someone says to you, what's the biological half-life of, let's say, technetium MDP, there is no answer to that. You have to say, well, what are you talking about? You talking about the biological half-life in the whole body? Are you talking about in the bones and the blood pool? Give me a reference point. So you have to know what your target is for biological half-life, either a particular organ or the whole body. And here's some things to note about T-biological. Number 1, if it's a radioactive compound, not only can it be calculated, but it actually has to be calculated because we cannot give enough mass of the radioactive element to measure directly and chemically how much is there. Like if we give technetium MDP, and take a little blood out, there's no way to measure the amount of technetium MDP in the blood. It might be picomoles, 10 to the minus 12 moles. We just can't do it. We have to do it mathematically, and we'll look at that shortly. But if it's a non-radioactive compound, let's say it's penicillin, and you're not allergic to penicillin, I could give you a gram of penicillin, could sample blood and urine, I could measure the biological half-life chemically. because a gram of penicillin is a lot. A few nanograms is way too tiny to measure with chemical processes. And here, remember what we said about T physical. It was boundless. The half-life could be anything, not with T biological. The biological half-life could be as short as seconds. What one study do we perform that has a T biological measured in seconds? What study? Anybody?
Xenon ventilation.
Perfect. We do a ventilation study. How long can that patient hold his breath? If we're lucky, 20 or 30 seconds. So the T biological is going to be seconds. Everything else is going to be hours, days, weeks, months, years, whatever it might be. So the range is typically seconds, hours, sometimes days. Usually more commonly it's hours, but it could be seconds to days. And finally, unlike T physical, there are lots of things that affect the T biological. For example, what can you think of? What can you think of that would affect biological half-life? Think about clearance from the body. So how about these? Here are some. How good is liver function? If the hepatic function is not good and drugs are cleared through the liver, you're going to have an extended or a longer than normal biological half-life. Renal function. You all know what a bone scan would look like in a patient with very poor renal function. It's not going to be a good quality scan. So we are counting on good hepatic and good renal function to give us a typical and normal biological half-life. Also, what do we do when we inject a patient for a bone scan? We inject them with MDP or HTP. We say, go away, come back in 3 hours. And during those 3 hours, drink a couple of large glasses of water. We want the patient well hydrated. We want to remove that background activity by urination and get that background out, so we'll get a high quality bone scan where we have a very high ratio of bone to background, bone to blood, bone to soft tissue. We want that high target to non-target ratio. So that's some things. The hepatic and renal function, level of hydration. There are interfering foods and medications. Think about a thyroid uptake and so many things that interfere with that. We interview our patients very carefully. Have you been to the sushi bar every day for the last 2 weeks? You don't want that patient having a thyroid uptake test. That patient swallowed so much seaweed and got so much dietary or endogenous iodide that it's going to depress thyroid function and give us an invalid test. So there are many interfering foods. We, in fact, tell people don't eat ocean fish for a few days before your test. Lake fish is not much of a problem, but ocean fish like tuna and salmon and things like that all contain iodine. What about interfering medications? There are many things that interfere with a thyroid uptake test. What if the patient has an X-ray contrast study with contrast media containing iodine? That could interfere from weeks to months with an iodine uptake test. Or what about someone taking Synthroid or some other thyroid blocker like Tapazole, or those kinds of things interfere tremendously. Also, a minor problem could be that if the patient's metabolic rate is abnormally low or high, that could also interfere with biological half-life. So those are the primary external factors that affect T biological. Now, excuse me, if someone asks you, what is the most important half-life for a radiopharmaceutical? Your answer better be T effective. In humans, that is the only one that really matters. Yes, we need to have the appropriate physical half-life, but the only one that really matters is T effective, because take a look at the definition. The T effective is defined as a period of time that it takes to reduce the radioactivity of either a particular organ in the body or the whole body to 1/2 of its original value. And that's because two things are simultaneously going on. Elimination is taking place through the kidneys, through the liver, possibly through the lungs if it's xenon, and also it's simultaneously decaying because it's radioactive. And those two play a huge part in determining what T effective is. And in fact, when we get way back in the lecture notes to internal radiation dosimetry, there's only one half-life in the dosimetry equation. That's going to be T effective because we have to consider both elimination from the body and the physical decay. So that is designated as T effective. And to calculate that, you of course have to know T physical and T biological, and you have to know them accurately. Now, let's take a look at some of the properties of T effective. Number one, we can measure it directly. Let's say we wanted to know what is the T effective of cardiolite in the patient's heart. So we can inject the patient with cardiolite. We can wait the required period of time. We can take like a Geiger counter or even use a gamma camera and just look at the activity coming from the heart at time 0 and at 10 minutes and 20 and 30 and 40 and 50 and 60 and whatever time is required. And in the meantime, when the patient needs to use the restroom, that is permitted and in fact encouraged. And so we know elimination is taking place. We know decay is taking place. By putting that probe over the patient's heart, we can determine the effective half-life of the heart or any other target organ. The range is typically minutes to hours, but it could be as short as seconds in the case of a ventilation study, and it could even be longer than hours. But this is where mostly we see it. Minutes or hours. I'm so sorry. Okay, so typically minutes or hours, and it can be affected by the same external factors that will affect the T biological. True or false? All drugs have a biological half-life, not just radioactive ones. True or false?
True.
That is definitely true. Look at any drug package insert, and it will use words like this. The half-time of clearance of this drug from the blood pool is X hours, or the clearance from the kidneys is Y hours. It'll give you biological half-lives. It might even give you the biological half-life of the whole body. So yes, all drugs have a T biological. True or false? The whole body biological half-life equals that of individual internal organs.
False.
False.
False. It's going to be totally different than any one of them, most likely. It might be coincidentally be equal, but pretty much it's going to be different. The whole body biological half-life doesn't equal that of individual organs. It equals the weighted average of all the organs in the body. So that is totally a false statement. How about this? T physical and T biological can never equal each other.
That's false.
What they say never, right? So yes, that is false. And in fact, if you take a look at technetium MAA, our pulmonary perfusion agent, the physical half-life is 6 hours. Totally by coincidence, the biological half-life of those microemboli in the lungs happens to be around 6 hours. And so never say never. In internal radiation dosimetry calculations, true or false, the most important half-life is T physical.
False.
False. Told you earlier, T effective. Now, how about this? At time 0, we have a radioactive patient. Let's say it's that cardiac. We want to measure the T effective in the heart. So we place a detector over the heart, and at time 0, the reading is 20 MR per hour. We've taken multiple readings, and the patient is permitted to use the restroom. And 2 hours later, the reading is dropped from 20 to 10. You know that's a half-life of some kind. True or false? That is a biological half-life of 2 hours.
Would that be the effective half-life?
That is correct. Was elimination taking place?
Yes.
Yes. Was decay taking place? Yes. So what you measured was an internal organ in the body at multiple points in time, and you discovered that 2 hours later, that reading dropped in half because both elimination and decay are taking place. Therefore, that is totally a false assumption, and T effective would be the correct answer. Okay, now, if you had your notebook in front of you, I would say put 2 stars by this slide and write, know this for the exam. And hopefully you have your scientific calculator with you today, or you might even have your cell phone, and we may need to use it a little bit here. Here's what this math relationship says. 1 over T effective is equal to 1 over the sum of the reciprocals of the other 2. 1 over T effective is 1 over T biological and 1 over T physical. Now, many people who teach this show a much more complicated formula, which is something like the sum of these 2 over the product of the 2. I don't recall because I don't work it that way, but this is so easy on the scientific calculator that I recommend working the problems with this equation. And so before we do that, if you will take out either your calculator or your cell phone and open up your calculator function and turn your calculator, if you have an iPhone, turn it sideways, and you should see a calculator that looks like this. Okay. And one of the keys that's on there, on mine, it's way over on the left side, is a key 1 over X. You might also have a key that's X to the -1, but most of them have 1 over X. And so that is the reciprocal key. And we're going to use it in a couple of minutes. And you're going to love working these problems this way. If it takes you 4 seconds, you're going slow. It's really very quick. Let's take a look first, though, at some special cases. If you have a special case where the physical is much greater than the T biological, then the T effective is always going to equal the really short one. Let's take an example of xenon. Xenon has a 5-day half-life, but number one, the T biological is very short, measured in seconds, and therefore the T effective is going to be measured in seconds. Did it matter if xenon was 5 hours or 5 days or 5 weeks? It didn't make any difference at all. This study is over in 2 or 3 minutes at the most. And here's the math to prove it. 1 over 5 days converted to seconds is equal to 0.000002. 1 over 15 is about 0.07. This value approximates 0, so you can see that the T effective equals the really short one. Now let's back up here. So that would be 1 over 15 seconds, T biological, plus 1 over 5.3 days, physical, equals 1 over X. And so in that case, and also in this extreme case, the T effective will equal the really short one. Here's the other case. Consider sulfur colloid for imaging the reticuloendothelial system. The physical half-life is 6 hours. How long is the biological half-life? It is forever. I've heard people say, oh, it never clears, therefore the biological half-life is 0. Not true. Biological half-life is infinitely long. It never clears. So in that extreme case, where T biological is much, much longer than T physical, then T effective equals to T physical, the very short one. And here's the math proving it. 1 over an infinitely large number is basically 0, and therefore T effective equals T physical. So in any special case where one of them is much longer than the other, if it's 50, 100, 1,000 times longer, you don't even need to work the math. It's going to be the shorter one. Now, here's a different special case, pretty unimportant in the big scheme of things. But what if T biological and T physical happen to be equal just by coincidence? For example, with MAA, the T physical is 6 hours and the T biological is 6 hours. And so we can simply say 1 over T effective is 1/6. Let's take a look right here. 1 over T effective would be 1/6 plus 1/6, which equals 1/3. T effective will be equal to 3. Now, we're going to need our calculators. And if you have any keystroke troubles, I'm counting on you to give a shout out so I'll be able to help you. And this is a sample problem off the board exam. Iodine 131 sodium iodide has a biological half-life in the thyroid of 24 days. Now you will note that you are not given the half-life of I-131. There are some of those that you're expected to know, and in the very first 10 minutes of the next lecture, next Thursday, we're going to cover the half-lives that I think you need to know. Who knows? What's the half-life of I-131?
8 days.
8 days, great. So let's set up our equation. 1 over T effective is 1 over 8 plus 1 over 24. Here it is right here. 1 over T effective is 1 over 8 plus 1 over 24. Now, if you'll take out your calculator, and here are going to be your keystrokes. Look on the bottom. 8, hit the 1 over X key. You took the reciprocal. Plus 24, hit the 1 over X key, equals, and then remember, your unknown is in the denominator. It's 1 over T effective. So you have to hit the reciprocal key one more time, and it should give you 6 days. So here's how fast that is. 8 reciprocal plus 24 reciprocal equals reciprocal. And you should come up with 6 days. Everybody able to get that?
Yes.
Good. Any keystroke difficulties? Anybody having a problem?
No.
Okay, great. I'll assume you all got that. Great. Here's another one. Technetium compound. Again, we're assuming you know the half-life. Has a T effective of 1 hour. What is T biological? Now here, we're going to have to do a little subtraction. 1 over T biological is 1 over T effective minus 1 over T physical. That's going to be 1 over 1 minus 1 over 6 is 5/6. Now, you don't really need a calculator. You could say 1 over 1 is the same as 6/6 minus 1/6 is 5/6, but we have to turn that upside down, and 6/5 would be 1.2. But just for practice, try this on your calculator. 1 reciprocal key minus 6 reciprocal key equals reciprocal key. And you're done in less than 5 seconds, and your answer should be 1.2. Okay, unless I hear somebody yelling and screaming, I'm going to assume you got it right. Now, this is a math problem just to give you a little bit more practice. Just for fun, it says, we would never administer a radiopharmaceutical where we know T biological and T effective, but we don't know the half-life. We would never do that. We always know the half-life. We always know the isotope. But let's just look at the math. We have, and look what it says, not the half-life, what isotope was used. So we know T biological is 4, T effective is 3.075. So 1 over T physical is 1 over 3.075 effective minus 1 over 4. Here are your keystrokes. 3.075 reciprocal minus 4 reciprocal equals reciprocal. And that's going to give you 13.3 hours. And if you know your isotopes, you should know that 13.3 hours correlates to the isotope of iodine 123. So one of the lessons to keep in mind here is you need to know the half-lives and imaging energy of the most important of the radionuclides. Okay, all right. Before we move on to decay constant, any questions from anyone about this formula? Anyone? Okay, good. Now, next is the decay constant. It has the Greek letter lambda. And we define decay constant as a number that represents the fraction of all nuclei that are decaying per unit of time. And by definition, lambda, the decay constant, is 0.693 over the half-life. Now, the number 2 for taking a half is hidden in there, but you probably are not aware of it. But this happens to be the natural log of 2. If you take your calculator, punch in the number 2, and hit the LN key, the natural log key, you'll come up with 0.693. So that's where 2 is in there, but this is a logarithmic function. So lambda, by definition, you need to memorize this, 0.693 of the half-life, or if you solve for a half-life, the half-life will simply be 0.693 over lambda. And we're going to work some problems with that very shortly. Any questions about that constant? Okay, good. Now, lambda is always expressed as a fractional number and a time unit to the -1 power. For example, 0.1 hour to the -1. This means the decay rate is, this 0.1 is 10%. That means the decay rate is 10% per hour. Okay. Now, lambda, you have to be careful here. Can lambda be 0? No. If lambda was 0, that means the decay rate is 0. Your isotope is not even radioactive. And lambda can't be 1 because that means 100% of it all decays in one moment. And we know that doesn't happen. Decay is logarithmic. So lambda can be any value greater than 0 and less than 1. That means it could be 0.1, 0.3, 0.5. It could be 0.99, but it can't be 0 and it can't be 1. And it's going to have this format: a fractional number and a time unit to the -1 power. Now, if I were making up your exam question, I'd give you this true-false question. You got 50% chance to get it right. The decay constant is 10% per hour, 0.1 hour to the -1, 10% per hour. True or false? After 5 hours of decay, at the rate of 10% per hour, 50% is decayed and 50% remains. True or false? What do you think? Anybody? So it sounds like a nice logical argument. You got 5 hours times 10% per hour gives you 50%. But a lot of things about decay that are logical are never, ever true. And this is one of them. Let's do the math in our head. The first hour, we go from 100% to 90, right? 10% decayed in that first hour, we went from 90. But in the second hour, 10% of 90 is now 9. It's not 10. Remember, the total amount that we're taking 10% on is decaying constantly. So after the first hour, we're down to 90. After the second hour, we're down to 81, and then down to 72 and 63 and 54 and so on. And so it's not at all going to be 5 hours. And if you want to know what it is, very simple. The half-life is going to be 0.693 over lambda. It's going to be 0.693 divided by 0.1. Hour to the -1 in the denominator flips up to the numerator. And it's going to take 6.93 hours to reach half value, not 5 hours, but 6.93. So that was, this question is totally false. You can't just do a linear extrapolation on it. Okay. The decay constant of an unknown isotope is this number, 0.01034, hour to the -1. What is the isotope? Now, obviously, you have to calculate what the half-life is, and then we'll determine what the isotope is. The math is really pretty simple. The formula is simply that the half-life is 0.693 over the decay constant. If you divide 0.693 by 0.01034, hour to the -1 flips up. We have 67 hours. And what has a 67-hour half-life? By coincidence, there are two isotopes. One is indium-111, and the other is molybdenum. What is the only purpose in this world for molybdenum? What do we do with it?
The generator to make technetium.
Good. So this is the parent of technetium-99m. It's in the generator. And how often do we intentionally inject molybdenum into patients? The answer, of course, is never. In fact, we do a Molly breakthrough test to make sure we're not injecting any significant amount of molybdenum. Okay. How about this? The half-life of an isotope is 220,000 years. That isotope, I'll tell you what the isotope is. That's going to be technetium ground state. What is the decay constant? Now, before we solve this problem, let me ask you a question. Let's say you underwent a liver scan. You were injected with 5 or 6 or 8 millicuries of technetium sulfur colloid, and we know that your liver can never clear this out. The biological half-life is going to be infinitely long, so the T effective is going to be based on the half-life of the isotope, which is 220,000 years. Here's the bottom line. You went home with a liver radioactive with a half-life of 220,000 years. Are you worried about that or not?
No.
No.
Great. It might sound bad, but the answer is no. And here is why you're not worried about that. What is lambda? Lambda is 0.693 over the decay constant. This divides out to be 3 millionths is decaying per year. And so you're not worried about that. No human could live long enough for this to be any contribution at all. It might add a tiny drop to your background. That's all that it does. So the isotope, of course, is a ground state technetium. You may or may not have known that, but that is what it is. And so we would never be worried about a half-life that long. Now, let's take this a step further. Which would you be the most worried about in your body? A half-life of 100 years, 10 years, or 1 year? Which would be the worst? Anybody? Yes.
100 years?
I don't think so.
So the 1
1
year.
year.
1 year.
Sure. So look, all of us, with God's help, are going to live at least another 10 years. So if you have a 1 year half-life and you go through 10 half-lives, 99.9% is decayed. Only 1 part in 1,000 is not. So if you have a 1 year half-life, you know that in your lifetime, all of it's going to decay. But if you have a 10 year half-life, you'd have to live another 100 years for all of it to decay. And I hope you do. I hope you do live that long. But you can see that the risk of 1 year is much greater than 10 years or 100 years, much greater. So that's just trying to keep things in perspective for you.
Is that more or less because the energy is all depleted in your body in that 1 year?
Yes, it's because all of the decays that are going to take place have taken place in your body. Remember, we're talking about something like something with a biological half-life that's infinitely long. This is even relevant to other things, but in the extreme case where we can't clear it out, that's when we would be the most worried about 1 year or a 10 year half-life. And so, yes, if you have a 1 year half-life and you're going to live 10 more years at least, then all of the decays will take place in your body. But if you have a 10 year half-life, then in 10 years, only half of it has taken place. So I'd be a lot more worried about a 1 year half-life than a 10 year. If the biological half-life, though, were 12 minutes, I wouldn't worry about it because it's going to end up in a toilet somewhere and not decaying in your body. So this is only the case where T biological is forever. In other cases, you have to balance everything else. Okay. Now, there is one more term. This one's a little bit complicated that uses the term lambda, and it's called the mean life. Now, if you have a series of numbers, let's say you have 10 numbers, what's the difference between the mean value and the average value? Got a one-word answer. Okay, anyone? So the answer is nothing. A mean value is the average value. So you might think of this as an average life, but we call it the mean life. And here's what it means. If you have a collection of nuclei, let's say you got a gazillion nuclei, the mean life means how long on the average, does every nucleus exist before it decays. Now, we all know that decay is constantly going on. It's a random process. On a decay curve, we know that it's coming down logarithmically. And so if we have a collection of atoms, some might decay in 1 microsecond, 1 millisecond, 1 second, 1 minute, 1 hour, 1 day, 1 week, 1 month. We don't know. All we want to know is what is the average length of time that all those nuclei exist before they decay. Not even 1% of them decay at the average lifetime, but we're talking about the average value. And we need that because the mean life is what's going to go into the dosimetry equation. In fact, it's going to be the mean effective life that's going into the dosimetry equation. So here's how we derive this. We know that lambda is the rate of decay. So if we take 1 over lambda, you might call that the rate of non-decay, or how long does it last? And so if lambda is 0.693 over T1/2, then 1 over lambda, the rate of non-decay would be 0.693, it would be T physical over 0.693, or 1.443 times T physical. That means that the mean life, how long do all the atoms last before they decay, would be 1.443 times the T physical. It's an isotope. Remember, an isotope only has 1 half-life. So if it's technetium, we would say simply 1.443 times 6 hours. That means that all technetium atoms last about, I think it's about 8.6 hours, all of them, and they decay. Now, we know decay is logarithmic. It doesn't do this where it's a flat line and then boom, everything decays in 1 moment. It never does that. So this gives you the average value. Now remember, an isotope only has 1 half-life, T physical. But what half-lives does a radiopharmaceutical have? Has all 3, right? Effective, physical, and biological. And so what we care about is the T effective. That's the most important half-life for humans, and especially for dosimetry. So someone has to be able to tell you what the T effective is, and then we can say the T effective times 1.443 is the average length of time that nuclide stays in the body before it either leaves by a biological mechanism like urination or decays. And so the T effective is taking into consideration both elimination and decay, and multiplying 1.443 times T effective gives you the mean effective life. Now, please note, I'm not saying the mean effective half-life. It's not a half-life. It's a mean effective lifetime, the average value that they live before they die, so to speak. Now, here's a couple of problems. What is the mean life of I-123? Now, this is an isotope. It's only got 1 half-life. You might recall 13.3 hours. Very simple math. 1.443 times the 13 hours. This is telling you that for I-123, on the average, every iodine nucleus lasts 19.2 hours, and then it's gone. We know that not even 1% lasts exactly that long, but on the average, all of them do. Now, for an isotope, simple math. But how about this? We already worked the first half of this problem earlier. We said that if we have iodine 131, T biological 24 days, what was the effective half-life? If we go back to that problem, I think you recall it was 6 days. It was 1 over 8 plus 1 over 24. That was 6 days. 6 days is the T effective. But this says, what is the mean effective life? So we're simply, remember, we worked it already down to here. We're going to say simply that the mean T effective, the mean effective lifetime is 1.443 times T effective, 1.443 times 6 days. So it, on the average, every iodine atom lasts for 8.65 days in the body, on the average, and then it's either cleared out by elimination or it's gone by decay. It's a very important concept, not so simple. It's an average value. Okay, let's see if you were really paying attention. What is the T effective of I-123? And I will help you with one thing. Choice A, the 13.3 hours, that is the correct value for T physical. But the question says, what is the T effective of I-123? Anybody?
D.
D like David?
Yeah, D.
You are correct. An isotope doesn't have a T effective. Unless you know both the physical and biological, there's no way to know what it is. What molecule is it? Is it technetium? Sorry, what molecule is it and what's the T effective? You don't know what it is. An isotope can't have a T effective until you know what the molecule it is, what the biological half-life is, and the T physical. There's no such thing. All right, we are nearing the end here. And I believe we're going to finish right on time at 11 o'clock. And so I want to show you another equation that is important to know. Pretty simple to understand it, really. The activity of a collection of atoms or nuclei is simply the number of atoms that you've got, that's N, times the fraction decaying per unit of time. I think that makes sense. A certain number of atoms, if half of them are decaying in a certain period of time, the activity will be a specific value. So remember, lambda is going to be somewhere between 0 and 1, but not 0 and not 1. And N is going to be a huge number because even a microgram of something contains 10 to the 18th or 10 to the 20 nuclei. It's going to be a huge number. So the activity is N and lambda. Now, we will always know what lambda is because it's going to be 0.693 over the half-life. We will always know what the activity is because we know how many millicuries we administered. So I want to show you where this is really a very important equation to know what to do. Let's say that you are a patient, you're hyperthyroid. The doctor says to you, I'm going to treat you with 10 millicuries of carrier-free iodine-131. Carrier-free means there are no other iodine isotopes present. That's what you want, ultra-pure I-131. And you say to the doctor, hold on, I'm allergic to iodine. How do I know that while you're curing my hyperthyroidism, that you're not going to harm me with that radioactive iodine? Don't forget, I'm allergic. So what you need to do is have a mechanism, an equation that will let you calculate what mass of iodine is associated with those 10 millicuries. And then you can say, oh, you know, that mass is 100 milligrams. I'm really worried. I'm not going to give it to you. But if that gram mass is only 80 nanograms, no problem, because all of us in our daily diets are swallowing about 100 micrograms every day with no problem whatsoever. So if it's under 100, 150, 200 micrograms, we're not going to worry at all. So there is this, here's our simple equation. And you will never have to do this on an exam, but I'm going to race through it just to show you how we came up with the 80 nanograms. What we need to do is determine the number of atoms. So we say that the number of atoms is A over lambda. Here it is, 10 millicuries divided by this value. That would be 10 millicuries divided by 0.693 over 8 days. I brought this down here as 80 millicurie days. I multiplied by the number of disintegrations per second per millicurie. So my millicuries cancel. There are this many seconds in a day. Seconds cancels, days cancel. And we are so far up to disintegrations. We make this simple assumption that it takes one atom to have one disintegration. Now we're at atoms. We use Avogadro's number and convert this to moles. And then we say iodine, 131 grams per mole, convert the grams to nanograms. And here's our answer. Again, you don't have to know how to do that. I just wanted to show you that the math is long, but not really very difficult, especially with a scientific calculator. So this computed to 80 nanograms. That is 1/1000th of what we are swallowing every single day. So you would say to the patient, I've done the calculation, and there is no way that this is going to harm any human, not even an infant. It's 1,000th or a 10,000th of what you're swallowing every single day. And there's, in fact, I shortened that equation. So if you use this formula and take your millicuries and multiply it by this factor and the atomic mass, there's your answer in a very short equation. Okay. It is 4 minutes to 10. That's enough time for me to offer you the opportunity to ask any questions that you would like, anything we've covered. And here's where we're going to start next Thursday morning, where we're going to review clinically useful nuclides. So I will open this up. Let me stop the screen sharing. I will open this up. If anyone has any questions whatsoever, please feel free to unmute yourself and go ahead. Anyone? Yes. Okay, no questions? Okay, great.
Professor Koresh? I'm
Yes.
sorry. So if we needed the recording of this lecture just to go over everything that you went over this week, could we get that from you? Or
Yes,
okay.
yes, you could. I'm not going to be able to give it to you for every single lecture, but if there's one, if there are lectures that you feel are difficult to understand, you'd like to review it, especially stuff with mathematics, yes.
Okay.
Get your program director to request it, and I'll send it to the program director. I'll send a link to a probably a Dropbox file, and you'll be able to follow it. You want just the audio?
Yes.
Okay, sure. That will not be a problem. So just ask your program director to ask me. I'll be glad to send it. Okay.
For sure. Thank you.
Sure. Any other questions from anyone? If not, I want to thank you for two things. Number one, for participating.
Dr. Karish, I'm sorry.
Yes.
I would like to speak with you when the students leave, please.
Oh, okay. All right. Sure. How about if I just give you a call on the phone?
Sure. Thank you. Bye-bye.
Okay.
Thank you.
All right.
I have a question too, Dr. Koresh.
Sure.
You had said that there were links to tests for the students. Did you send that out in an email or?
I did.
Okay. Can you resend that to me? Because I did not receive that.
Yeah, no,
Please.
yeah.
Thank you.
I know that some people have received it because I've seen people taking the practice tests and getting their score sheet. So I know some of the program directors got it, but yes, I'll send the links to all the program directors just to make sure you all have it.
Perfect. Thank you.
Any other questions from anyone? If not, I want to thank you for two things. Number one, for your attention during the presentation, and also thank you for participating. Teachers don't enjoy Zoom lectures very much when the participants never ask or answer questions. Yes, we're transmitting the information, but it's a lot more enjoyable for us when people participate, and I appreciate your doing so very much. And so unless there's any other question, I'm going to shut down the meeting, and I will see you at 9 o'clock Central Time next Thursday morning. The same link that you logged in today, you're going to log in for all 14 of the classes. So see you online next week. Have a good week.
Thank you.
Thank you.